So first of all, I want to thank the organizers for inviting me to this very nice workshop and to present my work. I realize I should have brought my spin talk, but I brought another talk, but it's still related to interfaces. This is work that we have done at Chalmers, and the main players in it is actually Mikael here, who started it up, and now he's working in virtual reality out in the industry, and his work is taken on by Patrick Holmwall, who has been working, let's say, 2 years on that. And Thomas Levander and myself are supervising the work. And it's going to be about D-wave superconductivity and what happens close to interfaces in that case. So I start out with posing a question, because if you have unconventional superconductors and you want to make devices, you need to go down to the Metascopic scale. But unconventional superconductors, we know, are very fragile to all kinds of scattering. So the question is if you even can do that. So the definition of Metascopic is, of course, that the atomic scale starts playing a role with the device size that you're looking at. And as I already said, then, that impurities and disorder would kill or reduce the unconventional superconductivity and also surface scattering. But this is, on the other hand, interesting, because most of these materials are strongly correlated, and if you can, by reducing the dimension, kill the dominant ordering state, you might get a peek on what other ordering is going on. And in fact, you can see if there is a possibility of competition, you might see what the leading loser is in that case. I'll make some references to experiments, and they were done in YBCO, and if we just look at the length scales of that, you see that the atomic length scales is a couple of angstroms, the coherence lengths a couple of nanometers, and then the system size can be like 100 nanometers or so. Usually they are larger, but you can bring them down now to 50 or 100 nanometers. And the initial motivation came from work at Chalmers, where they managed to set up a YBCO grain in a setup that they could actually control the current from a source to through this dot via the source and drain, and they could affect the transport by a gate. So this is what they did, and now you could start looking at basically single electronics in the sense. So what does an extra electron do on this island? And they brought it down to low magnetic fields and low temperatures, and they found some, let's see, there we go. They found some quite interesting results. First of all, they saw a parity effect, so you could see whether there was an odd or even number of electrons on the island. And that indicates that there's a full spectroscopic gap, because the tunneling is very slow, so any tunneling charge on it will explore the whole island. And then they have another interesting effect, is actually that this parity effect increases with magnetic field. And the scales here were very small, they're microelectron volts. So here's the typical free energy that is related to this parity effect, and this is the gap, the spectroscopic gap, which they got by looking at the IV curves, actually. This was published and was the PhD work of David Gustafsson in Floriana Lombardi's group. Now, if you go to D-wave superconductors, which YBC belongs to, there is a problem with having a parity effect, because if this red blob here should be the Fermi surface, then the gap has different magnitudes depending on where you are on the Fermi surface, and it also has different signs by the yellow and blue here. And in particular, you have nodes, so it means that a electron tunneling onto a YBCO island would always scatter up and end up in one of these nodes. This picture is sort of the Fermi surface here, and then I'm just picturing the gap. And this is the generic BCS D-wave density of states. Now, if you make a mesoscopic, you introduce surfaces, and if the order parameter is aligned to the surface like this, you even enhance the number of zero energy states, because this is actually a topological process where you go from one side of the order parameter to another. So it's just like going straight through a vortex, and you will generate a zero energy state which is located close to the surface. And what happens is, not only do you have the nodes, but you get a massive flat band of states on the Fermi level there. And these states, they basically decay out on the order of the coherence length in from the surfaces. So what happens when you make a mesoscopic D-wave is actually that most likely you're introducing more states on the Fermi level than only the nodes. So how do you get around with this? Now, of course, if you have a lot of states at the Fermi surface, what happens is that you are prone to all kinds of instabilities, because the system does anything to get rid of these states. And let me adjust the picture here a little bit. Oh, okay, I'll bring it a little bit closer. Okay, now. So if you have any residual interaction, and these are just pairing strengths as a function of some spin fluctuation model, you see that not only the D-wave, let's see, I have to jump. Okay, not only the D-wave pairing interaction is attractive, but also subdominant exists. And just due to this large number of states at the Fermi surface, you just need an infinitesimal strength, pairing strength, to actually generate a surface state in this. And they can come out in different pairing symmetries. Either you have this D plus IS, or it can be an D plus ID that we talked about earlier this morning. And not only superconducting instabilities are possible, you can also have magnetic or spin wave. And probably you can even think about other kind of instabilities. Now, we went back and analyzed this data, and using the possibility of just introducing a small S-wave at the interface. And what you find then, it nucleates due to this large density of states that you have. And actually what it does is it gaps the full Fermi surface. So instead of having all these states, you get a finite gap in the nodes all over the place. And you can do calculations just with a microscopic tight binding, or you can do it with a quasi-classics. What you find is that the tail of this proximity, or the proximity tail into let's call it the grain of the D-wave, actually is gapped. And the energy gap goes like 1 over R. So you quickly gap quite large islands like that. And there's another thing that I haven't on this slide, is that this subdominant S-wave actually grows with a small magnetic field, because it is really a slave on the D-wave order parameter. So you can increase the gap as you increase a small magnetic field. So that is all in agreement with this fully gapped state. And this we published in this PRL. Now, this is not the first time you have talked about having subdominant S-waves in D-wave. Quite in the end of the 90s, in the beginning of this century, there were evidence of this in tunneling, because the D-wave, the zero energy states, gives you a big zero bias conductance peak, and at low temperatures this one split spontaneously without a magnetic field. The problem with this is that this was seen in several experiments, but you should also detect a large magnetic field coming up, because there are large currents that come up when you have this time reversal symmetry broken state. And all measurements that they did came up with a null result. So it was not really conclusive what the situation is. You would see this splitting coming spontaneously at low temperatures, but you never saw a large magnetization of magnetic field. No evidence of that. So that's where we come in. We were inspired by the grains, and we were also really interested in seeing how can you do high performance computing with quasi-classics. And what we did is basically we looked at a grain. Now this looks like a washer. The hole in the middle is only in the first pictures. It's totally irrelevant. But you can make a grain, very regular in this case, and you look at the total density of states of that, and you get the V shape. And you start now computing what the order parameter looks like self-consistently. You take the simple D-wave structure, and then you can calculate the density of states of the whole island. There you have it. And if you introduce the pair breaking surfaces, you see that you get a reduction of the order parameter close to the interfaces. This is just a 45 rotation of this. And instead of having this V-shaped here, you now have this large density of states at zero energy. Now, what we found by a fluke, the student came back and said, I find this very strange thing happening at a given temperature. So the order parameter made a spontaneous transition from being real valued to actually having a phase that was winding close to the interface. And it happens very, very sharply at the T star temperature. And once it comes up, you can also calculate the current. So what appears here is actually that this winding of the phase gives you a superfluid momentum that comes up spontaneously. And it was so sharp, if you look at the current, it comes up at 0.18 Tc. Now this is a high temperature superconductor, so Tc is 100 Kelvin, so this is a large temperature. You can follow it like that. It looks like a second order phase transition. You can do the energetics, you can do the free energy, you can also do the entropy, and I'll show the heat capacity. And you really see that it has all the evidence of a second order phase transition. And the new order coming up is actually this superfluid momentum. This I said, but what is special with this, there's no additional interactions that I introduced to the system. This comes only with this basic D-wave pairing. So it's something that's happening spontaneously. No extra pairing channels or magnetic channels or whatsoever. Now there were a paper out from Anton Vorontsov who looked at D-wave superconductors ordered so that the surfaces of pair breaking in very narrow slabs. And he found a phase diagram that is very resemblant of what we see in the full de Ferrel if we take the S wave in a strong paramagnetic field. But instead of, here's the temperature, instead of having the magnetic field here, you have the inverse of the thickness here. So when it becomes very large, this value, the pair breaking kills superconductivity totally. But when it's large enough to have a little bit of superconductivity, then you get actually a modulated phase. This is what he found. And then as he made it thicker, he predicted that it would go down linearly to 0 when the thickness is infinite and you just have a freestanding surface. What we found is, of course, that we could reproduce his line here, but at a given thickness, which happens to be roughly 12 coherence lengths, then this becomes size independent. And you get this phase where you have this spontaneous superfluid momenta occurring at the interfaces. So why does it happen? Well, it happens, the energetics is actually that once you go into this phase, you get the rearrangement, so you move all the spectral weight out away from zero energy, and that is done by having, here I'm basically plotting, this is position along the surface, and this is in energy, and we're just putting the intensity of how many states you're having. So instead of having all the states on the Fermi surface, now they are inhomogeneously moved away from zero energy. And moving these states, of course, it gives rise to the currents, and you have large currents, zero current, and then they flow back. So you get some kind of fractional vortices happening at these interfaces. The spectra now is locally shifted by the local superfluid momenta that you have. And you can look at the spectra in different points, either a current node where there's zero current or where you have maximum current. And you can see here's where you have a current node. It's just the same spectra that we had in the beginning. But when you look where the current maxima, you have a maximum shift of this state. And the shift here is on the order of 25% of the full gap. So it's a large shift in energy, actually. So now our student Patrick started playing with the code and did some examples. We wanted to see how robust this one is. So first he made a D-wave snake. It looks like this. So he made a sort of a narrow ribbon of D-wave, but it increases in width as you go by here. And what he's plotting here is not the currents, but the induced magnetic field flux that you have along the surface. And what he's mimicking is actually he's going through along this line. So he's starting up here with a very narrow slab. There's nothing happening. And then suddenly you get these states where you have spontaneous currents, but they are homogeneous. And when you make it thicker and thicker, suddenly these alternating currents occur, and you get alternating magnetic fields in different directions. So you get a staggered magnetic field here. And again, the sizes here are on the order of 10 or 20 coherence lengths, so it's around 50 nanometers, 20 nanometers, somewhere there, depending on what D-wave superconductor you're looking at. You can make the shapes more irregular. So now this is the dominant crystal direction, and we know that the order parameter is pinned, so you have along different axes, you have different signs, and then you have the nodes at 45 degrees. So if you cut it like that, you still find this kind of state. You can make surface roughness. So now we're making mesoscopic faceting, so they vary like this. And then depending on how your surface is oriented here, you can have surfaces where you have basically no pair breaking, then you don't see these states coming out. But here you have a lot of pair breaking and you see a few. You can also actually play around with this when you have a freestanding surface here, that the net magnetic field, if you would put a squid there, is actually 0. So it adds up to 0. It's only when you have a very small facet that you get a net magnetic field. And in fact, there is a critical angle around 20, I was estimating it to 25 degrees, where you start getting this spontaneous currents, some fractional vortices. Patrick continued and looked how this system looks like when you start putting on a magnetic field. And here is 60 by 60 coherence lengths. And you put on a magnetic field that is just below when you have the first vortex entering into this system. And what you see is typical, now this is above this T star, is that you have the Meissner currents in here, and the Andreev bound states have a paramagnetic response to the magnetic field. Now you ramp up, or you move the temperature here, you have the same field actually, and what you start seeing is that the magnetic pattern starts getting modulated, and you see evidence that the surface currents, from being very homogeneous, they get some structure, and then when you go below, when you go below, then you have developed this kind of necklace of fractional vortices and flux patterns along the surface here. And if you look without the magnetic field, you see that these are of equal size, but if you have a small magnetic field, then you have screening currents, so you'll have a difference between positive and negative fluxes. Now you can make a discussion and look at the free energy. So we have different cases. We have the full line without a magnetic field, and here is where you basically have half a flux quanta over the area. And you see that you have this sharp transition between having the real valued order parameter and the one with the superflow or the superfluid momenta. And when you turn on the magnetic field, you still see that this bend over happens. And the phase diagram is quite robust for small magnetic fields. And interesting, you can calculate what the jump is in the specific heat, and we can compare it to what the bulk jump is when you enter into the D-wave superconducting state. And of course, this is a surface to volume thing, but for this particular thing, it's still on the order of 4.5% of the full gap. So it's a large jump in the specific heat, actually. And the state prevails. You can put in one vortex. You still have this pattern of vortices or fractional vortices on the surface. You can put 3, you put in 6, and it's principle when you flood it up with vortices and you establish a vortex lattice, then the screening currents will be strong enough to push them away. So it's quite a robust state. Now, in the beginning, I was talking about the fact that you could add a subdominant S-wave pairing channel, and this one is usually, we parameterize it, so we have the TC of the D wave, and then we say that if I didn't have the D wave, the strength of the S wave would give me this fractional TC. So that is a way to instead of talking of pairing strength, you relate it to some physical parameter. And now you can look at the temperature, and you can see where different phases occur. So we have the alpha phase, that's plain D wave, where we started. We can put in a weak, rather weak pairing, and we get this beta phase. And that's time reversal symmetry broken state. there's a d plus is, but still with remaining fractional vortices. And then you can make it very strong, and in the end, this one would win. So what I talked previously was was down on this line, and now I move up into these 3 points. And now you can look at the corresponding spectra. And the corresponding spectra are, if you are at this point with no subdominant, you get this peak, you get a broad peak. And this peak is now, you should compare it now to the coherence peaks of the D-wave, which is out here at roughly 2 kbtc. And here we would have like 0.5. So we see by having these currents on the surface, the zero bias peak is not temperature dependent in how it widens, but it's given by how the Doppler shifts are here. And this is actually what is seen in most of this NIS tunneling in D-wave superconductors, that you get a very broad zero bias conductance peak. If you are in the regime where you have a weak S-wave pairing, then you still have this vortex phase, or this flux phase around the surface, but now the existence of the IS actually makes the central peak go away. And this is very reminiscent of what was seen in the first tunneling data. And the nice thing with this is actually, if you would see the net magnetization due to this time reversal symmetry breaking state, there is no magnetization. It's very hard because it's staggered. So the net magnetization is actually 0. So this kind of state, I would claim, could actually have been seen way back, because you could have this splitting happening at a transition temperature and actually showing basically no spontaneous magnetization to be seen in experiments. And it's only when you really crank up this strength that you kill the surface states, and the subdominant S-wave wins, and you get this large splitting, but you also get enormous magnetic fields that should be measurable. Yeah, thanks. Okay, I have one last slide before the conclusion, and that is how should one detect this now. We had the tunneling that has been around, and I think what we have here is rather consistent with that. But in order to really say that this state exists, one should be able to measure these fluxes on the surface. Now you can make some calculation and estimate how large magnetization you have, and this is, you have typically some micro-phi naught per psi naught squared, and that would translate to a few millitesla. But the problem is, of course, that any scanning squid that we have would take in hundreds of these and have a zero net. So you need to go to very modern state-of-the-art. Either you have these scanning squids, which are done on top of elongated quartz tubes, which could scan, let's say, a square of 50 nanometers. So you would have a varying number of magnetic fluxes enclosed in the loop. So you should see the change as you move along. Or you can use these NV centers, which is even more focused, where you could measure the individual ones. So that is a quite advanced thing to do. Another thing that you can do is actually to see what the total magnetization is in this system. And it turns out that if at a given magnetic field, the total magnetization goes down as you go lower the temperature. And then when you enter into the new phase, you will see a kink. And this is something that should be possible to measure, actually. So there are alternatives. We're still working on finding more ways to possibly see this state. Fine. So then I come to my conclusions. The conclusion says that first, you don't need an additional interaction channel to break time reversal symmetry. If you have the case of a D-wave superconductor which is suppressed at an interface, it can actually spontaneously start developing a superfluid momenta. Then secondly, I think that with the old experimental data that's around on tunneling, these findings are actually quite consistent in the fact that you below, when you're going down to 20% of TC or so, there's no decrease in the width, which you would expect by just the thermal broadening, shrinking. but it's sort of fixed, and it's at a rather large value. And then finally, we see evidence that you don't need to have large magnetic fields that you should see by, let's say, more typical scanning squids, because the magnetic footprint of this phase is actually a staggered magnetic field. And then finally, there's some interesting experimental challenges in either using nanosquids or perhaps magnetic field measurements to detect this. So this has been published in Nature Physics, and we are also working on manuscripts that have been submitted or just ready in submission. With that, thank you a lot.